Good morning, everyone. So today we're going to go over the homework from periodic trends a couple classes ago and also talk about the periodic trends a little bit. So obviously you're going to need a periodic table for this to kind of work. And then let me delete this picture. So really quick, let's just go back through and talk about the periodic trends. So one, atomic radius. And what's going to be important for the assessment is to really know what the trends are. So atomic radius, as we move to the right across the periodic table, the radius decreases. As we move down a group, the radius increases. Okay? And that's pretty much just standard. That one's pretty straightforward. Then we have ionic radii. So anions are always bigger than the neutral forms, and cations are always smaller than the neutral forms. Okay? So then we have electronegativity. Electronegativity, as we move to the right, it increases. And then as we move down, it decreases. Now, here you have to be careful. You want to exclude the noble gases, the lanthanides, and the actinides from this trend, right? They do not count. Fluorine has a higher electronegativity than any of these, so we don't want to include any of these in the electronegativity trend, or any of the lanthanides, or any of the actinides. Right? You exclude them from the electronegativity trend. The next one is ionization energy, and it's going to be the same as the electronegativity trend. Now, since we didn't have class today, we are going to move the assessment back by a day, but there are exceptions to this. We do need to have more time to sort of talk about the exceptions to ionization energy, but generally, as you move to the right, it increases, and down it decreases. So let's go over the homework. So, using the periodic table, rank the following elements in increasing atomic radius. So, if you look at the periodic table, right, you'll see that it sort of goes like aluminum, and then carbon, oxygen's over here, and then potassium is on a layer or a level lower than aluminum, right? So here are the different levels, and here are sort of the left and rights. I always like to draw a little picture like this so you see. So as you move down, atomic radius increases, and as you stay on the left, atomic radius increases. So potassium's going to be the biggest. Right, then it would go aluminum, right, which is one level up and furthest to the left still. Then it would go carbon, which is one more level up, but still furthest to the left. And then oxygen is going to be our smallest. So increasing means you go from smallest to biggest. So oxygen, carbon, aluminum, potassium. Rank the following elements by increasing electronegativity. So we have, using our periodic table, right, we're going to draw a little simple picture. So we have sulfur, and then oxygen is directly above sulfur. Neon is over here, same level as oxygen. And then we also have aluminum, which is same level as sulfur, but over here, right? This just helps make your left and rights, up and downs, a little easier to see. Right? I always draw a little picture like this. So electronegativity increases as we move to the right. But it does not include neon. Remember, electronegativity excludes the noble gases. So the lowest electronegativity would be neon because it's excluded from that trend, right? It has like 0 electronegativity. Then it would go aluminum, sulfur, oxygen. This is the highest. The reason for that is because aluminum is the furthest to the left and the furthest down, right? So it's closest to the bottom left-hand corner as the lowest. Then you move over to the right, same level, sulfur, higher than aluminum. Then if I move up, sulfur is less than oxygen, right? So if you start here at aluminum, sulfur would be higher because it's further to the right, and then oxygen would be higher because it's further up. So that's how that one's going to work out. So what's the difference between electron affinity and ionization energy? So ionization energy is the energy required to remove a valence electron. Electron affinity, you can almost think as it being the opposite, is the energy required to add an electron to an atom, right? So they're actually the opposites. Now the equations, let's see, so this is ionization energy, would be like you're removing an electron, so the equation would look like that, right? You had a neutral atom X, you took an electron out of it, and now it's cationic. It's an imbalance of electrons and protons. If we think about electron affinity, it's the opposite, so you're adding that electron and you're making an anion. Now we have one more electron than we do protons. So just so you don't forget, EA is electron affinity and IE is ionization energy. Those are the shorthands I use for those. So does fluorine or iodine have a higher ionization energy? So fluorine, if we look at the periodic table, is up here. Then it goes chlorine, bromine, iodine. Right? The trend for ionization energy is that as we move down, ionization energy decreases. So the answer is fluorine has a higher ionization energy. And the reason for that is because if you think about it, right, the atoms get bigger as you move down. So fluorine, right, the electron that's getting taken out of fluorine is maybe coming from here. So we'll say that this is fluorine. Then for iodine, we'll say that the electron that's being taken from it is a lot further away. So here is the electrons that are being pulled out. So this is the electron, this is the electron. This is iodine, this is fluorine, right? So look, in fluorine, the electron is much closer to the nucleus, right? If the electron is closer to the nucleus, that means that they're more attracted to each other, right? If they're more attracted to each other, it's going to require more energy to remove it, right? More energy to pull this electron out because it's closer to the nucleus. For iodine, since the electron is much further from the nucleus, right? The valence electron coming off of that, the N equals 5 level in iodine, much further from the nucleus, the force of attraction between the two of them is not as high. So it's going to be a lot easier for that electron to come out, right? That's sort of the why of what's going on here. In each of the following pairs, circle a species with the larger atomic radius. So magnesium and barium. Magnesium is higher on the periodic table than barium. So barium's going to be a lot bigger, right? Think about the onion metaphor. As you move down, you add a layer to the onion. Barium is in the same group as magnesium, so you're going to be adding layers on as you move down towards barium. Sulfur and S2 minus, well, we know that the anionic forms are always bigger than the neutral forms. And we'll talk more about that in our next class, but that's sort of the trend. That's what we know. Here it's copper because the cationic version, right? The cationic version is always smaller than the neutral version. So here we have helium and hydrogen minus. So let's be careful about this one. So if we think about the trend, let's compare the neutral versions first. So helium versus hydrogen, neutral. So hydrogen's going to be bigger even when they're both neutral because it's further to the left, right? But then if you make hydrogen now compare itself versus its anionic self, we know the anion's going to be bigger than the neutral form. So if the neutral form is bigger than helium, the neutral form of hydrogen is bigger than helium, and the anionic form of hydrogen is bigger than standard hydrogen, obviously the anionic version is going to be bigger, right? So that's sort of how you do that. If you have two different elements and one's charged, compare both of them neutral first. So sodium versus chloride, they're both on n equals 3. What does this mean? This means the third row. So that's good because we can make a nice comparison. So it's going to be sodium because as we move further to the right, the atomic radius decreases. So for each of the following exercises, explain your answer. In each of the following pairs, circle the species with the higher first ionization energy. So lithium or cesium, as you move down, right, ionization energy decreases. Think of the onion metaphor. What that means is that the electron that's being pulled out of cesium is further from the nucleus. That means that the nucleus cares less about it. It doesn't take as much energy. So lithium's going to have a higher first ionization. So chlorine versus argon, which one's going to have a higher first ionization energy? The answer is argon, but we will learn about this more in the next class. The next class is going to be all about ionization energies. So don't worry too much about that one. Calcium or bromine. So we've got calcium and bromine are both on n equals 4. So they're on the fourth row together, which is nice. We can make a good comparison. As we move to the right, ionization energy increases, so it's going to be bromine. So again, sodium plus or neon. The answer here is most likely going to be sodium plus. But again, we will talk about that in the next class. So that's a next class thing. There's a lot more to ionization energy than just the trend. So don't worry if it's a little confusing. If you can make a nice clean comparison, then do that. So beryllium and boron, they're both on n equals 2. And this one is an exception. Again, we're going to talk about it more in the next class. But the answer is really beryllium, right? Now, it's an exception to the trend. There's 2 exceptions. That's one of them. So this is the first time you're hearing about it, but that's technically the correct answer. Okay? This is an exception. Okay, so circle the best choice in each list. Highest first ionization energy, carbon, nitrogen, and silicon. So this is a nice one. So we have carbon, nitrogen, and silicon, right? So the further up you go and the further right you go, the higher the ionization energy. That's going to be nitrogen. I drew this little picture to help with my up and downs, left and rights. The largest radius, so we have, let's see, what's it trying to tell me there with the S2? I think my document's a little Funky dunky. So this is largest radius. This should be S2 minus. This is chlorine minus chlorine. Okay, so then if we look at the periodic table, we'll see that there's sulfur, then chlorine. So in general, right, if we just compare the neutral forms, sulfur is going to be bigger than chlorine, which means that an S2 minus is going to be bigger than just the neutral form of sulfur. So if sulfur is already bigger than chlorine and the anionic form of sulfur is bigger than its neutral form, then probably the anionic version of sulfur is going to be even bigger than the anionic version of chlorine, right? Highest electronegativity. So we have sulfur, tin, and arsenic. Let's see, where's tin at? Okay, so that's nice. They're in a fun little diagonal. Let's erase this stuff. So we have, let's see, tin, arsenic, sulfur. That's going to be my little picture there. They're in a diagonal on the periodic table. So highest electronegativity, furthest to the right, furthest up. That one's straightforward. It's sulfur. The smallest atom, we have sodium, lithium, and beryllium. So this one's another fun one, I think. So we have sodium, lithium, beryllium, right? Smallest is going to be furthest to the right, furthest up. So that's beryllium. Largest atom, we have iron, cobalt, and nickel. They're in a nice row, so they go like this on the periodic table. Iron, cobalt, nickel. So the largest is going to be furthest to the left, which is iron. Lowest first ionization energy, we have potassium, calcium, and sodium. So this looks like sodium, potassium, calcium, just like that. So lowest first ionization energy is going to be furthest to the left, furthest down. So that's going to be potassium, right? Because the trend is that it increases as it moves to the right and increases as you move up. So it decreases as you move to the left and you move down. Okay, and so that was the review of periodic trends, right? I think it's really helpful if you draw out these little silly pictures to kind of help you go through it. There's going to be another worksheet for you to work on between now and next class. We're going to talk a lot more about ionization energy next week, and the test is going to be pushed back later because we missed a day of instruction, basically. So I hope you have a great weekend.